Welcome to the lecture, talk, discussion on big data in the time of artificial intelligence. This is your professor, Atif Fareed Muhammad. So, the big data term we are having for over a decade now, how big it is, does it matter? The question. There can be many more questions. Let's look into these questions in a little bit more depth. In the vast interconnected web of our digital age, big data stands as a colossal, ever expanding universe. It is not merely a collection of disparate points of information, but a living, breathing entity, constantly evolving and growing. In the era of artificial intelligence, big data is the canvas upon which AI paints its intricate patterns and draws its profound insights. Imagine, if you will, the countless data points generated by every Google search, each one a tiny star in the galaxy of information, illuminating the path for AI to understand and predict human behavior with an uncanny precision. Yet the value of big data is found not in the data itself, but in what we glean from it. Consider the humble smartwatch diligently collecting heart rates, sleep patterns, and steps taken. This constant stream of data is meaningless until AI algorithms transform it into actionable insights, nudging us towards healthier lifestyles. Similarly, in the realm of finance, AI sifts through the sands of transaction data to uncover the golden nuggets of trends and anomalies, enabling fraud detection and predictive analysis. However, we must not confuse the insights derived from big data as the be all and end all. They are tools, guides, but not replacements for human intuition and ethical judgment. Take, for instance, the use of AI in criminal justice, where algorithms predict recidivism rates based on vast datasets. While these tools can inform decisions, they must not become the sole arbiters of a defendant's fate. For true understanding of wisdom, where the wisdom actually comes from, the interplay of information and consciousness, data and humanity. Words of caution: kindly avoid thinking in SQL or SQL mode for this lecture time period, bare minimum. In the era of artificial intelligence, the temptation to rely solely on SQL or SQL or structured query language for data processing can be strong given its familiarity and widespread use. However, it is crucial to understand that SQL was designed for structured data and may not be the best fit for the diverse, unstructured, and semi structured data that characterize big data environments. Just as a painter would not use a single brush for every technique, one must avoid limiting oneself to SQL when working with big data. The reason lies in the nature of big data itself. Big data is not just about volume, it's also about variety and velocity. AI models thrive on diverse data types, from text and images to sensor data and more, much of which is not easily queried using SQL. By insisting on SQL, one might inadvertently constrain the types of data that can be processed, thereby limiting the insights that AI can generate. For instance, trying to analyze social media sentiment using SQL alone would be cumbersome and inefficient, whereas tools designed for unstructured data like natural language processing libraries would excel at the task. The iterative and exploratory nature of AI model development often requires flexible data processing pipelines. SQL's rigid structure can hinder this flexibility. Tools and language and languages designed for big data processing, such as Python with libraries like Pandas and PySpark, offer more agile and scalable solutions. They allow for easier data manipulation, transformation, and integration, making them better suited for the dynamic workflows of AI projects. Therefore, embracing a broader toolset beyond SQL is not just a practical necessity but a strategic advantage in the era of AI and big data. What you're looking at, it's your interpretation. Think about it. In the era of artificial intelligence, where we are discussing the use of big data as of today, the metaphorical buses that transport and process vast amounts of information are not the traditional rigid structures of yesterday or yesteryears, but dynamic, scalable, and versatile tools designed to handle the complexity and diversity of modern data. These buses came in various forms, each tailored to navigate the unique landscapes of big data in the AI arena. One such bus is a distributed computing framework exemplified by Apache Hadoop and Apache Spark. These frameworks are akin to a fleet of high capacity interconnected buses that can traverse vast data sets, breaking them down into manageable parts and processing them in parallel. This distributed approach allows for efficient handling of large scale data, much like a well coordinated public transit system, ensures smooth and timely transportation across the sprawling city. Another essential bus in the big data ecosystem is the data pipeline, built using tools like Apache Kafka or Apache NiFi. These pipelines act as dedicated routes, ensuring the continuous and real time flow of data from various sources to their destinations. Much like express buses that prioritize speed and efficiency, data pipelines enable the swift ingestion, processing, and analysis of streaming data, crucial for AI applications that require up to the minute insights. Additionally, cloud based platforms like Amazon Web Services, Microsoft Azure, and Google Cloud Platform serve as expensive interconnected bus network. These platforms provide the infrastructure and services needed to store, process, and analyze big data at scale. They offer the flexibility to spin up or down resources as needed, much like a responsive bus system that adapts to changing passenger demands. Lastly, the buses of data governance and management, including tools for data cataloging, metadata management, and data quality, ensure that the journey through big data is well organized and reliable. These tools provide the roadmaps and guidelines necessary for navigating complex data landscapes, ensuring that data is accurate, accessible, and compliant with relevant regulations. The metaphorical buses helping big data in the era of artificial intelligence are diverse and multifaceted, each playing a critical role in the efficient and effective handling of vast and complex data sets. Think about it. Now, this is a train. The metaphorical train system that facilitates the efficient use and expansion of big data is complex, interconnected network designed to handle the vast and varied data sets that fuel AI innovations. This train system comprises several key components, each playing a crucial role in the seamless transportation and processing of the data. The data ingestion engine act as bustling train station, where data from diverse sources such as social media, IoT devices, and transactional systems is collected and prepared for its journey. Tools like Apache Kafka and Apache Flume serve as the ticket counters and platforms, ensuring that data is accurately and efficiently loaded onto the trains ready for processing. The data storage solutions are akin to the sprawling rail yards and depots, providing the necessary infrastructure to house and manage the enormous volume of data. Distributed file systems like Hadoop Distributed File System or HDFS and cloud storage like Amazon S3 act as vast storage facilities, ensuring the data is securely stored and easily accessible when needed. The data processing framework function as a powerful locomotive, driving the analysis and transformation of raw data into meaningful insights. Tools like Apache Spark and Apache Flink are the high-speed trains capable of processing large data sets in real time, while traditional batch processing systems like Apache Hadoop, MapReduce serve as reliable freight trains handling massive data workloads with efficiency. The data analytics and machine learning platforms are luxurious passenger trains offering comfortable and sophisticated environments for driving insights and building predictive models. Tools like TensorFlow, PyTorch, and scikit-learn provide the advanced analytics and machine learning capabilities needed to extract value from big data, much like amenities and services that enhance the passenger's experience. The data governance and management tools act as control centers and signaling systems, ensuring that the train system operates smoothly and safely. These tools include data catalogs, metadata management systems, and data quality tools provide the oversight and regulations necessary to maintain data integrity, security, and compliance, much like the traffic control systems that prevents collisions and ensure timely arrivals. The data visualization and reporting tools are the scenic observation cars in trains, offering panoramic views of the data landscape. Tools like Tableau, Power BI, and Looker of Google provide the visualizations and dashboards that make data insights accessible and understandable, much like the observation decks that allow passengers to appreciate the beauty of the journey. The metaphorical train system for expanding big data use in AI is a well-coordinated network of components, each playing a vital role in the difficult terrain of big data and efficient and effective handling of the data within the massive data lakes by bringing data in the ponds and then later bringing data in the tubs and bringing it in a spoon for the consumption. For ingestion and storage to processing, analytics, governance, and visualization, this trained system ensures that big data is leveraged to its fullest potential in the era of artificial intelligence. Now let's compare the difference between the bus and the train metaphor in the big data and the artificial intelligence arena. The metaphors of buses and trains illuminate two distinct approaches to data management and processing. Each represents a different philosophy, a different era, and a different set of capabilities. Much like the evolution of human societies from nomadic tribes to settled civilizations, buses, with their flexibility and maneuverability, epitomize the more traditional ad hoc methods of data handling. They can navigate through the winding streets of disparate data sources, picking up and dropping off passengers, that is data, as needed. This agility makes them well suited for smaller scale operations where quick point to point solutions are required. However, much like the early human societies that relied on small mobile groups of survival, buses can struggle with massive scale and complexity of modern big data environments. They may lack the robust infrastructure and centralized coordination needed to handle the vast interconnected datasets that characterize our digital age. Trains, on the other hand, symbolize the modern industrialized approach to big data management. They operate on fixed tracks, representing the structured, well defined data pipelines that facilitate large scale data processing. Trains are designed for efficiency and high capacity transport, much like the complex interconnected systems that underpin contemporary societies. In the context of big data and AI, trains embody the distributed computing framework, data warehouses, and advanced analytics performs that enable the processing and analysis of enormous datasets. They provide the scalability, speed, and reliability needed to drive AI innovations, much like the infrastructure that supports modern cities and nations. Yet, the distinction between buses and trains is not merely about the scale and efficiency, it is also about the nature of the journey and the destination. Buses, with their frequent stops and starts, represent the iterative, exploratory nature of early data analysis. They are the tinkerers, the experimenters, trying different routes and methods to uncover insights. Trains, however, are the embodiment of purpose and direction. They have clear destination, the desired AI outcome, and well-defined path, the data processing pipeline. This purposefulness reflects the maturity of big data and AI technologies, where the focus has shifted from the exploration to targeted outcome driven analysis. In this sense, the evolution from buses to trains mirrors the broader trajectory of human history, from the exploratory nomadic past to the purposeful industrialized present. Differences between RDBMS and Hadoop. In the vast landscape of data management, relational database management systems, or RDBMS as we know, and Hadoop represent two distinct philosophies, each of which has its own approach to handling and understanding information. RDBMS, with its structured tabular data format and SQL querying, embodies a sense of order and predictability. It is akin to a well-organized library where books are neatly categorized and can be easily retrieved using a familiar indexing system. This structure provides a sense of comfort and control, permitting users to interact with data in a systematic and predefined manner. Hadoop, on the other hand, embraces the chaos and diversity of big data. It acknowledges that the world of data is not always neat and structured, but often messy, unpredictable, and vast. Like an expensive, untamed wilderness, Hadoop's distributed file system and processing framework allow for the storage and analysis of massive, unstructured datasets. It encourages exploration and discovery. Rather than relying on predefined schemas, the openness to the unknown reflects a deeper understanding and true insight, from which it comes embracing the complexity rather than trying to force it into rigid structures. Yet the choice between RDBMS and Hadoop is not a matter of one being superior to the other, but rather a question of what is most appropriate for the task at hand, just as different environments call for different approaches to navigation. Different data challenges require different tools. RDBMS excels in scenarios where the data is well structured and queries are predictable, offering efficiency and reliability. Hadoop, however, thrives on the realm of big data, where the ability to process and analyze vast unstructured datasets is paramount. The wisdom lies in recognizing the strengths and limitations of each approach and choosing the tool that best aligns with the nature of the data and goals of the analysis. Let's take a couple of examples. In the healthcare domain, the differences between RDBMS and Hadoop become starkly evident in the management and analysis of patient data. Consider a traditional hospital management system where patient records are meticulously organized in structured formats: name, date of birth, diagnosis, treatment plans, and so forth. RDBMS excels in this scenario, providing a reliable and efficient way to store, retrieve, and update patient information. The structured nature of RDBMS ensures that critical data is easily accessible to healthcare providers, enabling them to make informed decisions quickly. However, The healthcare landscape is evolving rapidly with an influx of unstructured data from various sources such as medical imaging, genomic sequencing, wearable devices, and social media. This data is not easily confined to a rigid structure of RDBMS. Hadoop steps in here, offering a flexible and scalable solution for handling these diverse and voluminous datasets. For instance, analyzing genomic data to personalize treatment plans or processing real time data where wearable devices are to monitor patient health requires the processing power and storage capabilities of Hadoop. By embracing the complexity and variety of big data, Hadoop enables healthcare providers to gain deeper insights, predict trends, and improve patients' outcomes in ways that were previously unimaginable. So, an RDBMS has a schema, speed, governance, processing, and data types. The schema is required on the right. Speed is reads as fast. Governor means standard and structured application on any given datasets. Processing limited, no data processing is done in the RDBMS. It's all derived information. Data types, that is structured, and if anything goes out of structure, that can spill out of the RDBMS. Hadoop has schema that's required on the read. Speed, writes are fast. Governance is loosely structured. Processing coupled with the data. Data types multi and unstructured. Let's look into an example together. In the dynamic landscape of AI and generative AI, Hadoop emerges as a powerful ally, much like a visionary leader rallying troops from grand conquest and rallying them as well. Its schema-less nature is not a weakness but a strength, permitting it to adapt and evolve with ever-changing data landscape. In the realm of AI, where data comes in all shapes and sizes, Hadoop's flexibility is akin to a master strategist's ability to adjust plans based on the ebb and flow of battle. It can accommodate structured, semi-structured, unstructured data, making it an ideal choice for the diverse data needs of AI and generative AI. The speed of write in Hadoop is another testament to its powers. In the fast-paced world of artificial intelligence, where real-time data processing can mean the difference between victory and defeat, Hadoop's ability to quickly ingest the process data is invaluable. It is like a well-oiled supply chain, ensuring that data is swiftly moved from the front lines data sources to the command center's AI models for analysis. This rapid data ingestion enables AI models to learn and adapt in real time, providing up to the minute insights and predictions. Hadoop is loosely unstructured governance. So technically, let me repeat myself. Hadoop's loosely structured governance, far from being a hindrance, is a boon for innovation. It encourages experimentation and exploration, much like a wise leader who empowers subordinates to take calculated risks. In the context of AI and generative AI, this freedom allows data scientists and engineers to test new ideas, iterate quickly, and push the boundaries of what is possible. It fosters a culture of innovation where failure is seen as a stepping stone to success rather than a setback. Moreover, Hadoop's distributed nature and fault tolerance make it a resilient and reliable platform for AI and generative AI workloads, like a well organized army that can withstand and recover from losses. Hadoop's ability to replicate data across multiple nodes ensure that no single point of failure can bring down the system. This resilience is crucial for AI applications where the loss of data or downtime can have significant consequences. In the era of artificial intelligence and generative AI, Hadoop's ability to scale is akin to a leader's ambition to expand territories and influence. As data grows in volume and variety, Hadoop can easily scale out by adding more nodes to the cluster. This scalability ensures that AI models have success based on the access to the vast amounts of data that they need to learn and improve upon. It is a testament to Hadoop's forward thinking design, which anticipates and embraces the challenges and opportunities of the future. In this grand conquest of data and AI, Hadoop is not just a tool, but a visionary leader guiding the way towards unprecedented insights and innovations. So, this is the thing that I just discussed in quite depth, the RDBMS versus the Hadoop. In RDBMS, the schema is required on the write, and in the Hadoop, it's required on the read. RDBMS reads are fast, Hadoop's writes are fast. And again, since I have discussed all this in quite depth, so I'll skip to the next and what we have there to learn from the understanding. The differences between the IT systems and Hadoop. IT systems can work in gigabytes, Hadoop can work with peta or zettabytes. IT systems have batch and interactive access to the data or whatever. Hadoop has batch. CRUD, create, read, update, delete. Reads and writes many times, the IT systems do. Hadoop does write once, read many times. The IT systems, the structure is static. Hadoop is dynamic because there can be structured, semi-structured, unstructured data present in one cluster of Hadoop. Integrity comes for the IT systems is normalization. In Hadoop, it's denormalization. Scalability is technically in IT systems non-linear. In Hadoop, it's linear. A scenario to understand the big data trucking company collects using what? Let's look into this in more depth. In the sprawling, interconnected world of logistics, the essence of a trucking company's existence is not merely the physical act of transporting goods, but the deeper narrative of facilitating the flow of commerce and connecting disparate nodes of human activity. This narrative, much like the philosophical explorations of Edmund Husserl and Martin Heidegger, reveals the underlying structures of experience and being. For a trucking company, the integration of AI and big data can eliminate this narrative, unveiling hidden patterns and optimizing the efficiency of operations. The phenomenology of trucking, as Heidegger might describe it, is not just about the truck's routes and deliveries, but about the lived experiences of the drivers and rhythm of the roads, and the interplay of countless variables that constitute the logistical ballet. AI, with its capacity to process and analyze vast amounts of data, can delve into the phenomenological realm, extracting insights that were previously obscured. By leveraging big data, AI can map out the intricate dance of variables, from traffic patterns and weather conditions to driver behavior and vehicle maintenance needs, creating holistic understanding of the trucking ecosystem. Ethnography, the study of people and cultures, provide another lens through which AI can optimize trucking operations. By collecting and analyzing data on driver behaviors, preferences, and challenges, AI can gain an ethnographic understanding of the human element in trucking. This insight can inform the development of more intuitive and user-friendly technologies such as advanced driver assistance systems or ADAS and predictive maintenance tools which enhance driver safety and satisfaction. Moreover, AI can use this ethnographic data to optimize route planning, taking into account not just the shortest path but also the preferences and well-being of the drivers. The narrative of trucking company, as Husserl might explore it, is a complex tapestry woven from the threads of countless data points. Each thread, be it a delivery record, a fuel consumption report, or a maintenance log, contributes to the larger story of the company's operations. AI, with its advanced analytics and machine learning capabilities can weave these threads into a coherent and insightful narrative. This narrative can reveal inefficiencies, predict future trends, and guide strategic decision making, ultimately optimizing the company's overall efficiency. In the realm of Boeing and being and time, or Dasein from the Heidegger, as Heidegger would put it, the integration of AI and big data in trucking is not just technological upgrade, but a fundamental shift in the way the company understands and interacts with the world. It is a move from mere existence to day to day operations to a deeper, more profound mode of being, a data driven, optimized, and strategically aware organization. This shift enables the trucking company to transcend the mere act of transporting goods, becoming instead a dynamic, adaptive, and deeply interconnected node of the vast network of global commerce. A scenario to understand the big data: GPS, speed, acceleration, stopping, normal, too quick, driving too close to the other vehicles. Let's look into this in more depth. In the gritty, no nonsense world of logistics, understanding big data in the era of responsible AI is like being the lone wolf, always one step ahead, always ready to make the tough calls. It is about using every scrap of information, every piece of data to make the right move at the right time. Take GPS data, for instance. It is not just about knowing where your trucks are, but about understanding their journey, their story. By analyzing GPS data, you can see the patterns, the routines, and the anomalies. You can tell when a driver is taking a route that is too risky or when a truck is making unscheduled stops. It is like being a silent guardian, always watching, always ready to step in when something does not feel right. Speed and acceleration data are like the heartbeat of your operations. They tell you when things are running smoothly and when they are not. A sudden spike in speed could mean a driver is taking unnecessary risks, while the slow acceleration could indicate a problem with the vehicle. By monitoring these metrics in real time, you can intervene before a small issue becomes a big problem. It is like being a seasoned investigator, knowing when to act and when to hold back, always keeping the bigger picture in mind. Stopping data is just as crucial. It is not just about knowing when and where your trucks are stopping, but about understanding why. Normal stops are part of the routine, but too quick stops could mean a driver is distracted or worse, impaired. By analyzing stopping data, you can identify potential safety issues and address them proactively. It is like being the protector, looking out for your drivers and your cargo, making sure everyone stays safe. Driving too close to other vehicles is a red flag, a sign that something is not right. It could mean a driver is aggressive or tired or not paying attention. By monitoring proximity data, you can identify these risky behaviors and take actions to prevent accidents. It is like being the enforcer, setting the rules and making sure everyone follows them. Because in the world of responsible AI, safety is not just a priority, it is a responsibility. Understanding big data in the time of responsible AI is about more than just crunching numbers. It is about turning data into insights and insights into action. It is about being the silent guardian, a seasoned investigator, a protector, and an enforcer, all rolled into one. It is about using every tool at your disposal to keep your operations running smoothly, safely, and responsibly. Because in this world, there's no room for error, no room for excuses. There's only room for doing what's right even when no one is looking. What standard technologies you will use? That's a great question. Think about it. In the era of artificial intelligence, ethical AI, responsible AI, moral AI, or any governance associated with that when we are working with the big data? Now, this is a great question. Ponder upon this. Hadoop ecosystem utilization. In the intricate dance of data management within the logistics company, the Hadoop ecosystem emerges as a finely tuned orchestra where each instrument plays a crucial role in harmonizing the symphony of big data. Let us begin with Apache Flume, a service akin to the diligent conductor ensuring that data flows seamlessly from its sources to the Hadoop Distributed File System or HDFS. Flume's robust architecture allows it to aggregate and move large amounts of log data from various sources, such as GPS tracking devices and IoT sensors embedded in trucks, into HDFS for storage and subsequent analysis. This efficient data ingestion mechanism is the first step in transforming raw data into actionable insights. Next, consider Apache Scoop, the virtuoso that bridges the gap between the structured world of relational databases and the unstructured realm of Hadoop. Scoop acts as the maestro that effortlessly transfers data between traditional RDBMS systems and Hadoop, ensuring that legacy data can be integrated into the modern analytics pipeline for the logistics company. This means that historical data stored in SQL databases, such as customer records and inventory management systems, can be seamlessly imported into Hadoop for comprehensive analysis. This ingestion and integration allows for a holistic view of operations, blending past trends with real-time data to optimize decision making. HCatalog enters the stage as the meticulous librarian, providing a centralized metadata management service that catalogs data stored in Hadoop. It serves as the comprehensive index, permitting various tools within the Hadoop ecosystem to access and process data efficiently. In the context of logistics company, HCatalog ensures that data from diverse sources such as driver logs, vehicle maintenance records, and route planning algorithms are organized and readily accessible. This organized approach facilitates the smooth execution of complex data workflows, enabling data scientists to focus on analysis rather than the data wrangling. Apache Hive and Pig step in as analytical powerhouses, each offering unique strengths in data processing. Hive, with its SQL-like interface, permits for familiar querying capabilities, making it easier for analysts to perform ad hoc queries and generate reports. For instance, Hive can be used to analyze historical delivery data to identify patterns and optimize future routes. Pig, on the other hand, provides a high-level scripting language called Pig Latin, which is ideal for complex data transformations. It excels in scenarios where data needs to be cleaned, transformed, and aggregated before analysis, such as processing raw sensor data from IoT devices to extend meaningful metrics. Apache Spark takes center stage as the versatile performer capable of handling both batch and real-time data processing with unparalleled speed and efficiency. Spark's in-memory computing capabilities make it ideal for real-time analytics, enabling the logistics company to monitor and respond to events as they happen. For example, Spark can process streaming data from GPS devices to provide real-time traffic updates and reroute trucks dynamically to avoid congestion. Additionally, Spark machine learning library MLlib allows for the development of predictive models and can forecast demand, optimize demand as well as optimize inventory levels and enhance overall operational efficiency. Hopefully this has been helpful. Another example is a bank. Let's look into that in a little bit more depth. In the vast interconnected web of digital age, the confluence of ethical AI and big data presents a profound opportunity to shape a future that is not only technologically advanced but also deeply humane. As we navigate the complex landscape of data-driven decision making, it is imperative that we approach this endeavor with a sense of responsibility and stewardship. Ethical AI, much like the guiding principles of ancient wisdom, reminds us the power of technology must be wielded with care, ensuring that it serves the greater good rather than merely advancing narrow interests. Big data, with its vast and ever expanding repositories of information, offers unprecedented insights into human behavior, societal trends, and environmental patterns. However, this wealth of information also brings with it significant ethical challenges. The responsible use of big data requires a commitment to transparency, fairness, and accountability. Ethical AI provides a framework for addressing these challenges, ensuring that data is used in the manner that respects individuals' privacy, promotes social justice, and fosters sustainable development. By embracing ethical AI, we can harness the potential of big data to create a more equitable and just society where technology serves as force of positive change. In practical terms, the integration of ethical AI and big data can manifest in various ways. For instance, in the healthcare sector, ethical AI ensures the patient data is used responsibly, exactly the same way in the banking sector. The ethical AI can ensure that a bank user's data is used responsibly, safeguarding privacy while enabling personalized services for the bankers to provide the banking customers or consumers. In the realm of urban planning, ethical AI can create smart cities that are not only efficient but also inclusive, prioritizing the well being of all residents with their banking needs. If the banks are now the embedded organizations within these smart cities, and they become one with the smart city rather than being an individual organization. Data acquisition, input, multiple user event feeds, browsing activities, search per time period. Now, this is an example that I would like you to focus on very carefully. User U1 at the time 0 visit the bank site. The sources which are needed here for the technology service provision within the banking system are server logs. User 1 at time 1 search for credit cards. The source is still the search logs which are hosted within the server logs. User 1 time 2 browsed banking services. This needed to be secured and saved in the web server logs. User 1 at time 3 saw an email sent link. Link advertising logs are the area where the sources should be aligned. User 1 at time 4 used OLTP or online transaction protocol. Needs to be secured in the web server logs as we have done at browse banking services. The same user 1 at time 5 clicked on an ad for some insurance. That is the advertisement logs. Click server logs. That's how the data acquisition happens for the banking system to look into. Data acquisition for the lending zone. The event feeds are the user events which are stored in the HDFS or Hadoop distributed file system. That when we apply the pig Latin or Hive, we actually remove the filter the irrelevant events, and then we can write using Pandas or scikit-learn or NumPy in the Python. We can project relevant event attributes, and that means tag and transform, categorization, and topic. Whatever the data acquisition coming in from the lending zone, we can work with it. And that goes into normalized events, which our banking institution or healthcare institution or logistics information maintenance system can take advantage of normalized events. The map operations work to map the resources which are needed. Data acquisition for the lending zone. Output, single normalized feed containing all events for all users per time period. User 1 time 0 is content browsing. The tag is web clicks for the bank user, by the bank user. Second user at the time 2 search query the category credit card, and it can go on to user 36 at time 36 when bank site page click category some product that they were trying to figure out how to work with it. Feature and target generation for the discovery zone. Feature summarizes of user activities over time window, aggregates, as I just mentioned, the summaries of user 1 and time 0, user 1, time 1, and all that jazz. Aggregates moving averages, rates, etc. over moving time windows. Support online updates to existing features. Targets are constructed in the offline model training phase. Typically, user actions in the future time period indicating interest, click through financial product offering the content, site and page visits, conversion events like deposit, withdrawal, quote requests, etc. for the car insurance and all that jazz. Sign-ups to newsletters, registrations, etc. are also handy when we are dealing with the feature and target generation using the discovery zone. So the feature generation for discovery zone comes handy with this architecture, aggregated normalized events, as we just have witnessed earlier. Normalized event 1, 2, 3, and it can go up to 9, for example. In the Hadoop distributed file system, the map 1 happens, and that's U1 event 1, user 1, the first event. Map 2 is user 1, second event. Map 3 is user 1, and the second event still. Reduce 1, all events from user 1 should be given as map to reduce because all user 1s are there. However, reduce to all events for user 2 can be extracted out as a separate altogether record, as you can see that I have user 2 event 2 and then user 2 event 3 and user 2 event 1 are mapped. So summaries over the user event history come into the feature set for us to work with. Aggregates within the window, time and event weighted averages. Event rates can come handy when we are working with this data set. The modeling workflow within the discovery zone, there is a training phase where the user event history happens in terms of data acquisition, which we just witnessed earlier. The target generation happens where we get the targets that this person has looked at the credit card. However, that person has only debit account with us, checking account with us, and there's no even savings account. Feature generation happens, the features are created, the model training goes with the weights applied, that this individual has seen more than 3 times the credit card information on our banking portal or the website, however does not have savings account and does not have the credit card. That happened within the last 3 days, for example, let's say. And the evaluation phase, user events, data acquisition comes handy with that, target generation happening on top of the feature generation, and the feature technically come in with the weights that 3 times this individual has looked at the credit cards, does not have savings account, does not have a credit card, also however have a debit account with us for a very long time or checking account. Model scoring goes on that, evaluation happens, and the offer has been sent out in terms of print or an email. Batch scoring for discovery results. Let's look into this in a little bit more depth. The user event history as comes handy within the data acquisition period. Feature generation happens on top of whatever we have created, that this is a bank user with only checking account. The weights are applied, 3 times wash the credit card information on the web portal, and the online serving system is informed to go and create some sort of email or some sort of phone call or some sort of letter to be sent to this individual. So component data process as time estimation, its data acquisition can happen the 1 terabyte per time period. Time estimation is 2-3 hours. It's Hadoop clusters. It can be on-prem cluster, by the way, on the premises. Feature and target generation can happen on 1 terabyte. Size of features window can happen within the 4 to 6 hours, and that can be overnight process if we are not using predictive modeling on top of it. Model training, that is technically the machine learning or AI algorithm applied, can process 50 to 100 GB in 1 to 2 hours for hundreds of models, because we are not working with only ChatGPT or Anthropic or the Llama or the NVIDIA or anything else, Google Gemini. Scoring can happen within the 500 GB in 1 hour. And why that is 1 hour? Because we are working with the bank data, which is the transactional data. That's why I said OLTP, online transaction processing, which goes into the data warehouse, which is OLAP, online analytical processing. And that's without using any large language models. They can still process some decent predictions. Requirements extraction process. It's a two-steps process. So as mentioned here, two-step process is used for requirement extraction. Extract specific requirements and map to reference architecture based on each application's characteristics, such as data sources, data lifecycle management, data transformation, capability infrastructure, data usage, all architecture components informed by goals to use case description. Security and privacy has a direct map. Aggregate all specific requirements into high-level generalized requirements, which are the vendor neutral and technology agnostic. I suggest you look into this in a little bit more depth. All right, the business intelligence. The big data edge from data warehouse extensive process and costs, data analysis, data cleansing, entity relationship modeling, dimensional modeling, database design and implementation, database population through ETL, extract, transform, load, or extract, load transformation, downstream applications, linkage to metadata, mainstream process. You can see that there are three diverse sources of data available. Extraction, transform, and loading is happening from schema extraction, schema matching, and schema implementation into a data warehouse, and that's where analytical databases work. So this is how the business intelligence is the methodology that is utilized in the current banking system, for example, or current supply chain and logistical systems, which needs the incorporation of responsible artificial intelligence to speed up the process. However, we can use our current legacy sources. That's why I decided to bring this data warehouse or big data edge here for you to know, because if you know something, you can create a better feature and algorithm on top of that. So if you see analytical databases, when go into the data mart, what exactly happens? In Hadoop, it goes and takes all the data, and that goes into the data marts for the answering the questions by applying the business intelligence as a standard. That happens in the cloud, can be GCP, Azure, or AWS. This is the data sources. This architecture shows the data sources, data integration, repositories, analytical access, and this is the legacy architecture. Legacy architecture means we are living and eating, breathing, sleeping in this architecture for over last 4 decades, or if I have not over exaggerated, last 3 decades. Enterprise has data sources which has customer, product, location, promotion, or promotions, orders, supplier, invoice, etc. That can be unstructured, informational, external, and that goes between the data flow and workflow within the metadata management, security and data privacy, system management and administration, and you can see all the details in the blue lines, which are the base up to access from data sources. Data integration happens, extraction, transformation, load, or application of the requirement, synchronization, transport, messaging, information integrity, and the list goes on. I suggest you to look at that because this is the legacy architecture. However, when we apply the big data on top of this, what happens? The data lakes come handy, and we work with the metadata management by applying the H catalog or Hadoop catalog, by applying the data repositories from Scoop, MapReduce, and single source using H catalog and Pig by dumping in the data repositories, which is the HDFS, Analytical Data Marts, and HCatalog. And that goes into Handy as terms as a business application, and that rolls over this way. These are the bridging between the data lake and the standard data warehouse. So this overrides, and this goes and works with all these, and technically incorporates all these. However, for unstructured, semi-structured, and non-structured data comes handy into the HDFS. And analytical data marts technically are based on data marts, and HCatalog contains metadata. So you have just witnessed a data lake implementation, and that's how it works. So the reference architecture, the extraction, is the application used to transfer data, usually from relational databases to a flat file, which can then be used to transport to lending area of data warehouse and ingest into business intelligence data warehousing environment. Here, the Sqoop is helpful. I have discussed Sqoop in quite depth, so I'm not going to go into detail. Transportation, we work with MapReduce and Pig, and since I have discussed that in quite depth, so I'll not go into that detail in length. Load and apply has staging, data warehouse, data mart, and the current BI, whatever the current business intelligence is there, or proposed BI, or proposed business intelligence powered by AI on top of big data. Synchronization, that's where the ETL process takes source data from staging, transforms using business rules, and loads into central repository data warehouse. In this scenario, in order to retain information integrity, one has to put in place synchronization checks and correction mechanisms. That's where HCatalog is quite helpful, by the way. Information integrity is currently there are no special approaches, so that means if you are working with a legacy system, and when you go to Hadoop, then it becomes legacy because you have applied the big data on top of your data warehousing, and when you apply the data lake, that is technically the current system on top of which you can apply the artificial intelligence to work with this reference architecture. And transport messaging can happen using secure file transfer protocol, and that is helpful in any and every aspect. So now let's look into this. We can actually work with it where Hadoop distributed file system, a reliable distributed Java-based file system that allows large volumes. Why Java-based? Because we have extensively used in last 3 decades Java before we migrated towards Python or Julia or something else. And there you go. The HCatalog, I have discussed that in depth, so I'm not going to go into this detail. And this is your reference architecture, which I just have mentioned in quite depth for your understanding, so you can look into this. I'm giving you a pause. You can pause the video here to look at that. Staging area, none required, eliminated. Extraction from staging, not required. Transformation, not required. Load to DW or data warehouse, not required. And this is the use of artificial intelligence, which has eliminated all these requirements. MapReduce. Now let me show you some MapReduce in a little bit more depth here. Map is input data key value pair. The key value, I have a name, then I have a house address. So if my name is coming in, then you can see my house address. If I am a patient, then I have some sort of disease or some sort of sickness that I'm going to go get taken care of, clinical system. So my name is still the key, but my details change in terms of the sickness or the disease that I'm going to taken care in the clinical system. So data collection happens split 1, split 2, split 3, split the data and supply multiple processors by having a map. You can see that the maps are those blue dots, and you can see that the other data sets have different colors. That has the purple, yellow, and light blue and all that jazz. So we reduce the information and we get the key value pair into a result. A cat, bat, dog, other words, map reduce how it works. Now look at that, split, split, split. You have split, you have mapped, then you combine part 0, part 1, part 2 are the results that you're getting after the reduce. Look at this one very carefully. Large scale data splits. Map key 1, parse hash, parse hash, parse hash have been done. And the reduce says say and count. So P000 and count 1 is telling us what is in it. Let's look into this a little bit more depth. There you go. This count goes here. The green goes here. This blue is different. This is different blue. Different data sets. Different data sets. I'll keep on clicking and it'll keep on coming. So I'm not speaking because I'm just showing you the exact how MapReduce works and how the count actually gives us the number of cat, dog, and whatever is in the given data set in terms of distinguishing features that we are working with. So I have skipped through the references. I would suggest you to conduct a little research on yourself, by yourself, sorry, not on yourself, on the big data used in the AI or the MapReduce implementation in the responsible artificial intelligence arena, and look into the details to see how you can work with legacy architectures, to legacy architectures, and to the modern architectures. Thank you for watching this. Hopefully you have learned something. Happy learning.